Hey, what's happening, guys? I thought today we could talk a little bit more about oscilloscope use and some of the different triggers and acquisition modes that are available on modern digital storage oscilloscopes. Now for today, we are going to use my Siglent SDS1202XE. It's a 200 megahertz dual channel scope. What we're going to talk about, while it applies specifically to this scope, will generally apply to other modern scopes. It may have a little bit of a different name, or the menu item might be in a different place, but most scopes will have the functionality that we're going to discuss today. Now, for our signal generation today, we are going to be using this device here, which is the STB3, which is oscilloscope demonstration board, and this was loaned to me by our friends at Siglent. So this is a nice board. It'll allow us to get a whole bunch of different signals. So let's just recap what we talked about in the last video real quick. Okay, I will put a link down below to our last video so you can go over it at your leisure. But basically, our oscilloscope is a simple test instrument that shows us two things. In the vertical axis, it shows us, in most cases, voltage. It can also show us current, it can show us dB, but let's just keep it simple and say it's going to show us voltage in the vertical axis and time in the horizontal axis. So our oscilloscope shows us voltage over time. So if we look here, we are at 200 millivolts per division. So if you here's our zero line. So that line right there is 0 volts. So we come up here, this is 200 millivolts, 400 millivolts. That would be 600, let's say that's 500 millivolts total. And then we have our horizontal axis. Sometimes I just can't talk. And we have 200 microseconds per division vertically. So there's 200 microseconds, 400 microseconds. So for the first 400 microseconds, we are at 200 millivolts. Then for the next 2, 4, 500 microseconds, we are at 2, 4, 500 millivolts, a half a volt. See how that works? It's voltage over time. And that is very much an oversimplification of what's going on, because if we really zoom in here, you can see that that transition is not instantaneous like it looks. What are we at vertically? 200 nanoseconds, there's 100 nanoseconds. So there's 50 nanoseconds. So it is taking, let's say, 50, 60, about 70 nanoseconds to transition that voltage. Now we can be more precise about that. We can use our cursors. Come on. There we go. And measure that more precisely and say that we are actually reaching that in 118 nanoseconds. So that is the actual rise time of that signal, even though it looks instantaneous there. So anyway, voltage over time, that's our recap. That's it. Let's take a look at this signal here. If you look up here, you can see this is a 10 megahertz square wave. But it doesn't look like our last square wave, because there's this activity going on here, and there is this activity going on there as well. That's called ringing. And what it is an unwanted oscillation there. When it is switching from the low state to the high state, it's oscillating. And if we zoom in, you can see it even better. So the signal climbs, it overshoots where it wants to go, then it undershoots, and then it overshoots, undershoots, overshoots. What's happening here is the signal is underdamped. This is dampening here. See how it's very high, then lower, and then lower, and then finally lower. And then it finally goes to where it wants to be. That's known as dampening. So this is called ringing, and it simply means that your signal is underdamped. And it can be quite substantial. Now, if we look here, and let's bring out our cursors once again. This time we're going to use them to measure our voltage. I got them reversed, pardon me. Let's bring them in here. I like using cursors for measurement. It just lets me feel like I'm in control of something. Okay, so our peak-to-peak you're seeing here, the automatic measurement of 464 millivolts, but our actual peak-to-peak wave that we're looking at is 334 millivolts. Now, let's adjust this to the amount of ringing we're seeing going on here. Oops. And let's see how substantial that overshoot actually is. So on the positive, we're actually looking at 110 millivolts of ring. So a tenth of a volt might not sound like much, but it can definitely add up. So that's something to keep in mind. If you see that in what you're looking at, now you know what it is. Okay, what we're looking at here is a 25 megahertz sine wave. And if we bring up our measurements, you can see we're looking at a peak-to-peak of what, 126 millivolts, period, blah, blah, blah. That's not important. What we want to talk about here are our different acquisition modes. Remember I talked about before, the digital oscilloscopes work by sampling. This isn't really a line. This is a bunch of dots. Let's see, if I go in here, can I actually make it dots? Yeah, here we go, vector. Dots. That's what we're really looking at here, are dots. And if we zoom way in, you can actually see those dots. Let's zoom in for you to see them. Now you see that? That's what is actually happening here. This is the oscilloscope. Let me stop this. There we go. This is the oscilloscope sampling, period. Boom, 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 boom. Notice how it's doing that? And if I bring that out some, you can, whoops, you can see it there as well. Now I'm going to turn it back on, and those are just the dots coming together. So that is how the digital oscilloscope works. It is sampling. Now we're going to go back to vectors here. Now we have different modes that we can sample in. This is the normal mode, which just means it samples some dots and then it lays them out on the screen. Now we also have a peak detect mode, where for every sample it takes the highest point and the lowest point out of a number of samples, and it averages, well, yeah, it doesn't average them out, but it shows you kind of a difference between them. Then we have the average mode. Now if you take a look at the average mode, notice, okay, let's go back up here to the normal mode. Notice how you have kind of a thickness there to the waveform, and when we come down to average mode, it averages that all out and kind of gives you a cleaner, better picture. Now we also have this Aries mode, which is a high-res mode, and we're going to take a look at a feature of that. Let me get it set up here. Hold on. Alright, what we're looking at here is a square wave with kind of an ugly alternating duty cycle. But we can go into our acquisition mode here and bring it down to our high res and see how that kind of cleaned that up for us. You can see the duty cycle still fluctuating, but it's cleaned it up. If we go back to normal, then there's peak detect, then there's average. See how the average is aliasing there? But when we go to that high res mode, it kind of cleans things up and straightens them up for us. Okay, the signal that we're looking at here is an AM signal, amplitude modulation. Meaning that while the frequency of the signal remains the same, the amplitude changes, and that's a modulation. What we have here is a carrier wave, okay? And on top of the carrier wave is the modulation, and this modulation contains information. Remember that. Modulation contains information. This could be voice, it could be data, it could be continuous wave. It doesn't matter. Some sort of information is contained within that modulation. And it can be adjusted however you see like that. But one of the things I want to show you here is one of the really neat features of this scope, and that is called persistence. And if we turn persistence on, I think I just turned it off. There we go. What you'll notice is that in certain areas, it'll get brighter. And what we can do also is we can turn on color grading here. And you can see the very bright lines. There's some up there, there's some right there, and then right here where all these crossings are, all those nodes, those are the areas that are getting the most information. So that can be a really useful thing to have a look at, and that's persistence and color grading, a really neat feature of a lot of your more modern scopes. Now, some of the cheaper scopes aren't going to have that, but most of your modern ones will. Alright, what we're going to talk about here is the simplest type of trigger to use, which is the edge trigger. And in fact, if we bring up our trigger menu and we bring up the edge trigger, it tells you it triggers on a rising or falling or both, and that's really all there is to it. So let me zoom out here. Nope, we're all the way zoomed out. Okay, so as I bring up the trigger level, once the trigger level is within the waveform, it will simply trigger on it. So what it's doing is it's just looking, in this case, where we at? Rising slope, rising edge. So as soon as that trigger line, and that's indicated here, or as soon as that edge crosses that trigger line, then our scope triggers. That is just about the simplest way to trigger. Now, something that looks very similar to the edge trigger is the slope trigger, but it's just a little bit different. Let me set up a signal for that, and we'll take a look here. 1 second. Okay, so I'm giving it a slope signal here. Mainly it's just a square wave type thing. So what we're going to do is we are going to set our trigger type, in this case, to the slope. And you can see a trigger when an edge crosses two thresholds, inside or outside. Alright, so we have our rising slope, falling slope, rising slope, and a range, oops, wrong knob, about 200 nanoseconds, I think, for this. And all we have to do is dial it in. There we go. So now we're triggering on the slope, which has, in this case, about a 200 nanosecond time. And if we zoom out here, we can again bring in our cursors. Bring that in a little bit. I think I'm backwards. Yeah, it was. Anyway, that's how the slope trigger works. Pretty simple. Okay, what we're going to look for this time is the burst trigger mode. And if you watch real closely here, you'll see some blips. They're kind of hard to get. Let's see if we go capture in a single shot. Let me adjust my trigger a little bit. There we go. So there is a burst. Now I'm just using edge trigger on this. So this is not how you want to do this. But what I'm going to do is I'm going to measure this. Let's see, measure, type what we want to see. Here's yeah, so what we want to measure here is basically the period. Do with cursors here. So you see we're getting 560 nanoseconds. So what we can do is we can go back into our auto mode, then come over to our trigger, setup, and we will do a pulse, positive, limit range, is less than or equal to, whoops, less than or equal to, we're what, 560 nanoseconds? Is that what it said? Now I don't remember. So we'll set this here, and now if we get a burst, we should be able to put it on a single shot mode, and there we go. Now we can capture it using the pulse type trigger. So that is another trigger mode that's really useful for non-repeating periodic signals. Okay guys, in this case we're going to look for what's known as a runt pulse, and if you look closely in there you can kind of see them. Now you see what we got here is a square wave, and yeah, it's just really hard to see it in there, but every once in a while you see it popping. And no matter what I do with an edge trigger, we just can't key on those runt pulses. A runt pulse is a glitch where it doesn't cover the same voltage range as the rest of the signal. It can be a positive going runt or a negative going runt. So, to trigger on that, we're going to bring in our trigger menu, and the type is simply called runt. And now you can see there's our runt pulse right there. So you can set your polarity, whether you want positive or negative, your range, and then you can also set your upper and lower limits. It's pretty simple, and that way you can see your runt pulses, what they look like. You can bring in your cursors, and you can measure them. So you can see we're getting about 320 nanoseconds or 3.125 megahertz on the runt pulse. Just something pretty simple. Runt pulses. Alright, the final thing we want to talk about is serial decoding. And this scope can do I2C, SPI, UART, line, and CAN bus. We're just going to talk about I2C decoding. And the setup is in the trigger. You see we have type is serial, protocol is I2C. My signal is for channel 1. My clock is on channel 2. And then we have our decode here. You can see our data right there is in hex. Let's see here, format hex. We can turn our format to ASCII, and it should say Siglent, and it does. You can see it says Siglent, and there are some changing numbers after it. It's really simple to set up. We can even do a single shot, so you can take a look at that right there. You can zoom in. You can see this is our clock signal. This is our data signal. And if we come back here to our trigger, I can't even talk sometimes. Protocol is I2C, our signal. Okay. So channel 1 is the clock. Our threshold is 320 millivolts. So you can hit that. You can adjust. That's our threshold for channel 1. Whoopsies. And then there's our same threshold. There we go. Our threshold for our data. We got them set just like that. And we just put it in normal mode, and it'll trigger, and it will decode. That also works for SPI, CAN, line, and UART as well. So that's pretty smart. Now, like I said, most of your modern scopes will have that. Some won't, but it's really easy to use, and it's a nice feature to have on board. So there's a little bit more about using your oscilloscope. How to use some of the different triggers, what the different acquisition modes mean, and how to set up some serial triggering. I hope that helped you guys out. If it did, please give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. Big thanks to all the patrons. A big thanks to Jason Chonko at Siglent for helping us out with the demo board. And a big thanks to you guys for watching. That's it. I'm out. Peace.